I'm very happy to be here presenting this work, which is joint work with Nicholas Berkman from here, from UCL. So I don't have to spend too much time on motivating error correction and fault-tolerant gates, such as transversal gates. I just want to tell you that the main goal of this work is to look for good codes with transversal logical gates. And by good, the properties that I have in mind are such properties like LDPC or high rate encoding. And so that's what designing this family of code is about. Okay. So the way I'm going to go about this presentation is to jump right into the definition. And at this point, I ask you to keep an open mind. If the definition seems a bit strange, it will make much more sense as we go on. Then I'll recall what properties we might want of a CSS code to have transversal phase gates, and see why this family pin codes satisfy some of these properties. And then I'll present some concrete examples with numbers and everything, and also some ways to use these codes to get to distillation protocols or stuff like this. Okay. So to introduce the definition, I'm going to make it first very pictorial, and then we'll set the proper definition. So just imagine you have a gigantic pin board in front of you, and you have a bunch of pins that you can pin on the board. So maybe I have some red pins, I put them on the left. Also some green one, I put them in the middle, and some blue one, I put them on the right. So you could have, here I have 3 different sets of pins, but I could have more, just for the drawing. And in each set, I could have a different number than 2, just for the drawing, there's 2 here. Now the structure that we're going to put on this set is that of a relation between these sets. So I'm going to, for each color, I'm going to pick a pin and then attach it to some other guys from other colors. Okay, and for some reason that will become clear later, this is called the flag. So I attach some kind of string, I don't know, to, let's say, the pin 1 in the red category, A in the green category, and alpha in the blue category, and I call this F0. So I do this a bunch of times. So let's say I have three such tuples that are represented this way. And this is really the basic structure that we need to define the code, these codes. Okay, so let's put some more rigorous notation here. So I picked a number of different sets, which whose number is going to be related to a parameter analogous to a dimension. So in the example, I had d equals 2, and then every time I choose d plus 1 sets that I also call levels. And they were these red, green, and blue sets. Inside these sets, there are the pins. And the index of the set a pin comes from is called its rank, right? So for example, the pin B came from the set green. Okay. And then on this set, I put a relation. So relation, what is it? It's a subset of the Cartesian product of all the sets. And in the example, I had three such elements. This F0, F1, F2. So each element in this relation is called a flag, and as I just said, it's a tuple of pins, one coming from each set. Okay, so now I'm going to define 2 more structures. So the first one is what I'm going to call a type. It's just a selection of a subset of the different level of pins. For example, I can say, oh, I'm only going to consider red and blue. So this is the type red and blue. And given a type, I can construct what I call a collection of pins. It's just some pins coming from the selected level by the type. So for example, if I choose the type red and blue, then I could choose the pin 1 and alpha in the previous example. So this, thanks to this object, I'm going to be able to define subset of the flags. Okay, and that's sort of the meat of the structure here. So let's see how this works on a drawing. So I'm going to construct what I call pin set, okay, which is indexed by a type, so a subset of the levels, and a collection of pins, so pins coming from the same levels. So here I'm going to construct the pin set of type green and of pin B. So what it is just all the flags in my relation such that on the level green, they have this precise value B. Right? So in my example, there's two. There's this F1 and this F2. Okay. Now let's do a second example to be more clear. So now I choose this other type, so red and blue, and these two pins, 1 and alpha. And so I want all the flags that exactly have the value 1 and alpha on the level red and blue. So in this case, there's just one guy. There's just this F0 that does this. Okay. So this structure is pretty handy for this reason, because these pin sets have two nice properties. So first, they intersect nicely. If I have two different pin sets, and I look at their intersection, turns out it's either empty or it's another pin set. So it's fairly intuitive to see this. Basically, to be on the left pin set, you have to have the correct value on the type T1. To be on the right one, you have to have the correct value on the type T2. And so if you're in the intersection, you have the correct value on the union of these two types given by the union of these two collections. And then if these two pin sets disagree on some level, then this is empty. So this is the first nice property of this pin set. And the second one is a decomposition one. So if I look at one pin set of type T and collection S, then actually I can split it into disjoint union of other pin set. And basically the intuition is that I can split the flags in my pin set according to what's their value on some other level that were not pinned. Okay. So thanks to these two properties, I'm going to be able to basically prove all the rest that I can prove, that I will need to prove. Okay. So now we are almost there to define actually some codes. So up until here, my relation F was whatever, just a subset of the Cartesian product of these sets. So I'm going to be able to define a CSS code, I'm going to have to enforce some commutation relation, so I have to put some condition on this relation. And the condition is the following, is that my relation has to be such that if I pin all level except one, then the number of flags in that pin set has to be even, and for every choice of type and of collection. If I have this, I have a very nice, I can use the previous properties to show that if I take two pin sets, one that pins X level, another one that pins Z levels, and such that the sum of X and Z is smaller than D, then the intersection is going to be even. So okay. So now I'm sort of trying to give it away. So now given such a relation, how you put a code on it, the idea is to pick two integers X and Z, which are no greater than D. And then for each flag in the relation, you associate a qubit. And then the X stabilizer generators are given by all the pin sets where you pin X levels, and the Z stabilizer generators are given by all the pin sets where you pin Z levels. Okay, and we just, if this relation has this property, we just showed that then these are going to commute. So it's a valid CSS code. Okay. So this is the definition. Now let's see some examples and get a better feeling. So color codes are a specific case of pin codes. All right, so we've seen in a few presentations already what are color codes. So let me just make a drawing in 2D and recall what's it in general. So what you want some D manifold, and then you want that it's triangulated. So you put that it's triangulated by D simplices. And the other property that you need is that the vertices are D+1 colorable. So in 2D, that's something like this. So this represents like the hexagonal lattice. and you have some triangulation of the plane, and the vertices are of 3 different colors, and they don't intersect between the same color. And then you put a qubit on every triangle or on every disimplices in higher dimension, and so here the analogy with the pin codes is pretty straightforward. So your different sets of pins are actually the different set of vertices of different colors, and then your relation is just given by the triangles that you see on the graph. Okay, so having this this connection in mind, we can sort of think about how are we going to construct general pin codes. So we just need to find this relation with these strange properties that if you pin everything except one level, then you have even number of things. So let's see how do you build color codes in general. So if you read Hector Bombin's paper until the end, you'll find a method to construct color codes in arbitrary dimension, which is called inflating. So here I'm going to present this method in a slightly different way. I'm not going to inflate vertices and such, but this is strictly equivalent. So let's say I want to construct a color code in 2D. What I can do is I take any tessellation of my 2D plane, and I'm going to put on this 2D plane the flags of the lattice. So that's where the flag name comes from. So what is a flag? A flag is a tuple comprising one vertex, one edge, and one face, such that they are all adjacent to one another. And so because I have like a vertex, an edge, and a face, it looks kind of like a flag. So I think that's where the name comes from. So okay, here I put one. If I put all the flags of this square lattice, some of you might recognize that I have like some kind of octagons around vertices, some squares around edges, some octagons around faces. This is the 488 color codes. So if I put qubits on the flags and I have checks associated with vertex, edges, and faces, then I have my 488 color code. So what have I done this? I've done basically I just realized that if I put different set of pins given by the vertices, the edges, and the faces, and then as relation just the adjacency relation, actually I have a pin code relation. So this is this. But this works for more general structure like this. So what's a lattice of a Eugen space? That's actually, you can see it as a chain complex. So I have a space where I put the vector space using the faces, vector space for the edges, and one for the vertices, and then sort of the adjacency relation, I can view this as the boundary relation, whose property is that if I take the boundary twice, then I get 0. So another way of representing this is just putting dots for a basis of these spaces and then edges when they are related. And now what's a flag in this picture? This is just a path in this graph going from top to bottom. And then now I can, so as I say, I'm going to choose my sets to be, my pin set to be these different levels. And so the flags go from top to bottom. And so why is this a pin correlation? So if I pin everything except the middle level, say, then the number of paths going from top to bottom is going to be even thanks to the property of this boundary map. So that's why it works for like lattices, but now I can just put any chain complex and this still works, right? So I can go a higher dimension and have some wilder object that don't describe a 2D or certain dimensional object. And I would do the same thing. I choose a basis for each space, and then I put the lines according to the boundary relation, and then this define my flags, and then they have the property that they are pin code relation. Now, so this is sort of the first method to get pin code relation and possibly define codes on them. Now, if you want to construct color code, you can go another route, which is there's a nice way to build regular lattices, which is using the group of symmetries of these lattices. So there's a construction by using Coxeter groups where which have been classified. So they are the groups of symmetries of these lattices, and you can find only the lattices that are correctly colorable. And there's a prescription then to define the code in terms of the cosets of this group. So I'm going to skip a bit quickly on this. But basically, you can do exactly the same thing for some wilder groups. So if you are any finite group generated by elements with even order, then you can do a similar construction and get a pin code relation. Okay. All right, so let me quickly talk about transversal phase gates. So I'm going to write down omega L as the 2 to the L's root of unity, and then RL the corresponding phase gate. And by a general phase gate, I mean a gate that acts diagonally on the computational basis. And what it does, it puts a phase, which is given by omega L to some polynomial, which is called a weighted polynomial because every monomial is weighted by a corresponding power of 2. If you look at such gates, you can nicely know in which level of the Clifford hierarchy they belong to. So this is an example for L equals to 3 and 3 qubits. So for example, if you have the degree 3 monomial, you have CCZ, so with the correct weighting in front. If you have degree 2, depending on the coefficient, you have CS or CZ. Okay, so now what we want to do, we want to apply transversally this rotation gate on the qubit of our code, and we would like that it preserves the code space and that it does something on the logical level. So this is a way of writing down the computational basis state of a CSS code, where G is the generating matrix of my X stabilizer, and L is the generating matrix of my X logicals. And then I can just apply the rotation to every qubit and see what turns out. So what comes out is some phase, which is a power of this omega L. And what is this? This is the Hamming weight of whatever this vector is. So you use some identities. You can split this into 3 parts. So there's a part involving only the logical variables that you can put in front. This part will hopefully do your logical gate. And then there's 2 parts involving the stabilizers. This you would like to disappear to preserve the code space. Okay, so we have to just take a closer look at these three quantities. So one sufficient condition that you can apply to your codes for this to go well is, for example, if this quantity is involving your stabilizer, if they vanish mod 2 to the L, then you're good, then it disappears. So this is, in this case, you would have an exact transversal gate. Now you can settle for a weaker condition. So if instead of vanishing, they're just equivalent to twice weighted polynomial of lower degree, then you would just have a level L-1 correction to do. So maybe we can consider this case also. And then every time when some of these conditions are satisfied, then your logical operation is given by this first quantity after possible correction. Okay, so just slightly more on these things. If you can develop them and see that they are directly weighted polynomials, and their coefficients are given by overlap of the generators of either your logical, your stabilizer, or overlap across logical and stabilizer. Okay, so now I can formulate 2 conditions. So this is a sufficient condition, it's not necessary, to have a transversal gate on my code. So the first one is like exact transversality. So I split this into two aspects. The first one is just on the stabilizers. So they have to form something called an L-even space. And the other thing is on the stabilizer and logicals, their overlap has to have a sufficiently high power of 2 Hamming weight. And if you have this, then your transversal RL on the physical does something on the logical level, which is given by this polynomial. Okay, so what's this L-even space? So when I write L-even space, I just mean that every vector in this space has Hamming weight 0 mod 2 to the N. Okay. Now, now let's look at the weaker condition because that's easier to satisfy. So the weaker condition is just telling that my X stabilizer now they don't form an L-even space, but what I call a L-orthogonal space. And then the intersection between X logical and X stabilizer, it's just so if you choose at most L of them with at least one logical and at least one stabilizer, the overlap always has to be 0 mod 2 and not more than that. And then you would have your gate up to some L-1 correction. So what is this L-orthogonal space? So it's just a weaker version of L-even space. Now I just require that if I take the intersection of vector in this space up to L vectors, then it's always 0 mod 2, this intersection. Okay, so are pin codes good for this kind of properties? So my answer is partially yes. So the first very nice thing is that, okay, let's take a pin code relation on D+1 level, and then look at the X pin set, so the pin set that pin X level as a vector space. So if you do this, you can easily show that this is actually a D over X orthogonal space. Okay, so if X is not too big compared to D, then you can have some high orthogonal space in there. Now the second condition is more tricky because you need to have control over the overlap of logical. So unfortunately, I don't have it completely. I just have this one. So if I pick one logical operator and I complete with stabilizer operator and look at the overlap, then this is always 0 mod 2. But this is not true, no longer true if I take two logical operators, and this is a problem. So for example, if you want to make T gates, something just outside of the just third level Clifford hierarchy, then you would need this type of condition, but you also need two logical and one stabilizer to have even overlap, and this we don't have automatically. But I mean, it's a start. Okay. So now let's look at some actual examples. So these things can live in real life or at least in computers. So we've built, as a sort of first step, we've built hyperbolic 3D color codes using this Coxeter group construction. So for example, we've looked at the lattice 535, and then which looks like this when you put a color code on it. And then you have to do some tricks to put it into a finite size. And so, but we could, for example, find a code such as this one, so about 7,000 physical qubits and 5,000 logical qubits and distance 4. So the rate is pretty impressive, not so much the distance. And then this is like max stabilizer weight 120 for the X stabilizers, but that's okay. So one thing is that now there is this intuition with the color codes associated with like manifold that you would have this property of transversality. And for this hyperbolic 3D hyperbolic space, actually with the example we have, we could just check it, and this is actually not true. So a virtual code, if we check if every two logical and one X stabilizer, is it always 0 mod 2? No, that's not true. So if you have 3D hyperbolic color code, it's not guaranteed that you have transversal T gate. So which was a bit surprising at first, but I think it's linked to the fact that we don't really understand the homology of 3D manifolds. Okay, so now let's look a little bit at the other approach, which was the chain complex approach. So I've read papers about hypergraph products, so I know a way of building chain complexes. Just pick any matrix and then take the hypergraph product a few times, and then you have a chain complex. So we've done this to build D equal 2 and D equal 3 examples. So basically go over all the small binary matrices and look at what you get. And another thing that you can do to more easily build code with higher D is just if you take only levels of even size, then you can always put the complete relation as your flag relation, and this is always going to be a good relation. So those are these 3 examples, but they're going to be in the plot, the next plot. Okay, so if I just plot whatever I got here, this is number of physical qubits, this is number of logical qubits. Sort of the trend that we see is that the rate is pretty great, but often the distance is not so good. And then we have this, using higher dimension, we have this code that looks better, like distance 8 or 16. So, okay, but also for these ones, if we check, okay, does the condition 2 logical and 1 stabilizer overlap is 0 mod 2, does it hold? Most of them, like, the answer is no. Like, some of them, okay, if you have only 1 logical qubit, like this guy, then yeah, you're fine, but, okay. All right, so now let's try to make something useful in terms of doing non-Clifford gates. So one other thing that you can do is that if you have access to 3 tri-orthogonal spaces or triple even spaces, then you can puncture them, and this gives you a T-distillation protocol. So for example, this is described in this Haar and Hastings paper. So let's say G is a matrix which is tri-orthogonal, meaning that every triple of rows, when I overlap them, this is 0 mod 2. Now if I put this matrix in standard form like this, and I just remove all these first columns, these k first columns, then I can treat this these rows as x logicals, and these rows are x stabilizer, and this code will have transversal T doing transversal T dagger on the logical space. Okay, so in this paper they do it on the Reed-Muller code. So the Reed-Muller code is a pin code, okay? So it's represented here on the left. So if you take this chain complex with 2 elements per level and then put the complete relation, this gives you Reed-Muller codes. And then we've tried to slide variation to try to find some other codes. So these are the variation that seem to work the best, but I don't have any reason for why this would be good or not. And so if you take these codes, and so you look at the 2-pin set on these codes, and then you puncture them randomly, then you can get these parameters, which are pretty nice. So you get some distance 4 with some okay rates. If you look at the gamma parameter, which is often looked at in these protocols, we don't beat Haar and Hastings. We didn't even find the best that they found on the Reed-Muller one, but it's probably computing time. Okay. And now, last construction that you can do, then I was made aware when I discussed with Rangaswamy from Duke. So they have some nice work on transversal gates and phase gates. So I encourage you to go talk with him or download his poster abstract, so poster 46. So in their work, they have a prescription on how to get code with transversal phase gates using Reed-Muller code that I can actually just plug into pin code. So what's this construction? So you pick some D, and then you pick the X, which is D plus 1 over L, and then you're going to choose the X minus 1 pin set for your stabilizers, and just the X pin set for your X logical. So here we want to have control over the logical, so we just choose what they are, and then you complete this to whatever the Z should be. And then if you do this, actually this X number is chosen such that you're going to have all the correct properties for your transversal gate to preserve the code space. And also this is just big enough for the X logical. If you take L of them, then the overlap will not be 0 mod 2. So the gate you're doing will be non-trivial and in the else level of the hierarchy. So if you do this construction on these codes with the appropriate dimension, then you get a bunch of small codes such that if you do transversal T on them, then you get on the logical level some wild circuit of CCZs, which you can figure out what the circuit is just by looking the overlap between logical operators. So I didn't do it, but so this is at least something. Okay, so with this I think I'm going to conclude. So to summarize, so I've presented this family of CSS codes that we call pin codes, which is pretty vast. So this is also not necessarily super nice because there's a bunch of bad codes in there, but which is also pretty large, so it's pretty nice. So there's a lot of codes to see. Okay, they have these codes. They have multi-orthogonality properties for free, which is sort of what they're designed for, and then you can use them to massage them into finding distillation protocols or T2CCZ things. So more features that they have that I didn't talk about here. So since they are so closely affiliated to color codes, actually you can put the gauge code version on them similarly as for color codes, and this works in similar ways. They also have somewhat of an unfolding procedure where you take this this code and you sort of extract subcodes that give you some of the logical of the code. But we don't have like exact equivalence. We just find some of the logical operators by doing this unfolding procedure. Now, if you want to play also with boundaries in color codes, there's an equivalent notion for pin codes, and this is amounts to sometimes not pinning not allowing to pin on certain pins. Okay, so what's next? I think the main thing here would be to find to restrict the family to a good one. Because right now it's a bit wild, and there's very few control over the logical operators, for example. And then maybe, okay, if you can do, maybe you can do something without restricting, but maybe you need to restrict to have a finer study of what the logical operators are, and so have a better understanding of what the distance of these codes could be. And then once you have this, you can start thinking about decoding, and probably using analogy with color codes will provide some hints for this. So with this, I would like to thank you and welcome any question.
Thanks, Christophe, for a very nice talk.
Hi. Do you have control over the weight of the stabilizers? How do you, if I did want to produce an LDPC code for this, how do I restrict?
Yes. So this is directly given by the relation f. So basically, you want, for example, if you think of the chain complex picture, if the boundary relation is sparse and the length of the chain complex is fixed, then you know this is LDPC, right? But this is in general, you have to put constraint on this f. In the case of these Coxeter groups, the LDPC-ness comes from the fact that the size of the coset is always finite, and so so this is something which is also a property of the relation, and it's not given a priori.
I have a question regarding your general definition of pin code. So,
yes.
Do you have any examples of CSS codes that are not pin codes? So it looks to me that every CSS code should be a pin code.
So I don't think this is the case, because they have this property that the space, the stabilizer they form are whatever d over x orthogonal. So this, you can find spaces that don't have this property. So I feel like they are pretty large, but they are constrained to having a lot of orthogonality within the stabilizer space.
But do you have some examples of codes?
I mean, take the Tori code. Tori code is not a pin code,
oh, okay.
Right? So, or maybe, okay, maybe you can always make it trivial by making d equals 1. I'm not sure.
Yeah. So maybe you can just use X stabilizers, Z stabilizers, and qubits as three sets, and
I don't think so. Okay, I would have to think a bit more to find a clear example, but I feel like this is not.
Okay, and I also have a question regarding your examples when you showed some codes with distance equal like 16,
yes,
or something like that. So my question, what is the weight of the stabilizers for those codes?
So here we can compute them because, okay, so in this first case, so basically you're pinning two things, so you have to multiply all these numbers except 2. So this is 2 to the 2 to the 5 for for the biggest thing, and here this is going to be 2 to the 4 for the biggest one. And then you can play a similar game here.
Okay, thank you.
Any other questions? Actually, I've got the one. Could you comment on unfolding? Will you get some sort of a toric code?
So you get, not really, you get just some homological codes, which as far as I know, I don't see directly a nice structure in it.
But it will be like 3 vector spaces and a chain
Yeah.
complex. Any other questions? If not, let's thank Christophe and all the speakers of today.